All right. Before I start, any questions, concerns? Everything crystal clear? Yeah, so clear enough. Okay, so let's see, kind of doing the whole thing. Well, all right. Okay, so today I have three models I want to go through because they illustrate just some different characteristics of these systems that we're looking at. The first one is something called reneging, which is kind of a strange word to apply to it, but it kind of makes sense. And then I'm going to look at a simple, I want to call a simple machine failure model. And what's important about that is that it has what's called a finite calling population. Up until now, anything that has like an arrival process or Poisson process-like thing has implicitly assumed what's called an infinite calling population. No, I'll get into that when I talk about the model. And then the final model of today is a tandem queue with blocking. And we'll talk about what that's about. So we have blocking, balking, and reneging. So that's as extra little goodies to this. So first about reneging. Reneging is about, well, are you familiar with that term just in common usage? Renege it's when you make a deal, but then don't follow it. So which is now you can see how it applies here. What happens is, again, in part of what I'm talking about, this iterative modeling process, is that we start with simple models, and so far even these are fairly simple. And ideally start with the simplest model that does something like what your system does, but then don't stop there. Just kind of look at your system and compare things that you observe about it or imagine about it and what the model is doing. And if there's a significant dissonance between the two, then you want to upgrade your model. So what we notice if you watch these waiting line things is that one of our implicit assumptions has been that if somebody joins the queue, then it's the Hotel California. You know, you can check in, but you can't leave, right? And then when you observe these systems, you notice that sometimes somebody is waiting in line, and then they're kind of checking their watch, and then they say, "Ah, screw it, I'm out of here," and they leave the line. You see this, right? You've all seen this. Maybe you've all done this, right? You know, kind of. So it's like that restaurant that nobody goes to anymore because it's too crowded. Okay, so that is not captured by our model. And so if you're interested in the properties of the system, you might, if this is your business, as it were, then you might be interested in how much business are you losing based upon this. A more an application kind of in the sensor realm is that if you're kind of tracking certain targets, sometimes they kind of leave, and so it can be applied in certain, the concept at least can be applied in certain situations like that. Where anyway, but the idea is that we have everybody's impatient, and I mean, I am, you are. What does that mean? It means I'm not going to wait on this line forever, right? None of you would wait on a line forever. At some point, if you didn't get served, you'd go, you'd leave, right? So now how long? Maybe some are more patient than others, and so it's like internally we have kind of a clock that's kind of keeping track of our impatience, and then you know, when it kind of hits the leaving point, then we're out of there. So yeah, I mean, and you may, I don't know anybody who can sort of name that time. Like I'm willing to wait for 3 minutes and no more, not a second more. Well, you know, who knows? But that's something that we observe. So we want to capture that in the model. Okay, so we want to capture the fact that customers will actually leave in the model. And what this brings up is the fact that it brings into focus the fact that in our models so far, we haven't been keeping track of the individual customers. We've only been counting them. Now, we took a little step toward that in the last class where we were explicitly estimating the times in the queue and the times in the system. And there we were kind of representing our customers as their timestamp, that is when they showed up to the system. So we could try to do something like that here, but it becomes a little bit problematic. But regardless, we're going to do it a little bit differently. So now, in terms of our model, then just that's all the information that we need. That we have a certain, well, we have our usual, what I call the usual suspects, the number of servers and the service times. But then we're going to have an additional set of values I'm going to call the renege times. And what that is, for each succeeding customer, that's going to be their impatient time. That's how much time they're willing to wait online. And as soon as that time gets reached without service, then they leave. Okay, so. All right, so now let's look at some state variables. So again, our usual suspect of number of available servers is, which is initially K, and that's something we've been using. And all of these could be flipped with the number of busy servers and stuff like that. But here now, kind of informed a little bit about what we did yesterday. Now we're going to have a container, and all I'm going to be able to do is just, I want to keep track of the customer IDs. So I want to, so each customer that comes in is going to have a unique number. All right, and I'm going to put those in a queue, kind of the way we did with the service times, with the arrival times yesterday. And well, you know, what am I interested in? I'm interested in, well, of the potential customers, and given that this is going to be driven by an arrival process, that's going to count how many potential customers there are. So that state is taken care of. But the two quantities that I would be interested in, and they're in a way, if I know the total number from my arrival process, so one of these is redundant, but they're internally not redundant though. So I want to know how many customers, how many potential customers actually did receive service, and how many customers reneged. So those are the quantities of interest. You know, why? Because I want to know how many am I, if I were to, well, how many am I losing based upon this? You know, what can you do about any of this? If I don't like the number, again, like if people are going, hey, the lines are too long, I'm out of here too much, then, you know, what can you do? I mean, there are only a handful of levers that you can pull with systems like this. Basically, you can either hire more servers, or, you know, buy more machines, or get more resources, or get faster resources. So we could train our servers to serve a little faster, for example, or we could upgrade our machines to work faster. You know, those. But other than that, you know, when it comes to these queues themselves, we don't have a lot of leverage other than that. Okay, so now let's just sort of look at some of the events here. So we start with our run event. And so we, this first in, first out queue, now this queue is a data structure queue. So we initialize the number of available servers, and then the number served and the number of rigs are going to start at 0. So, okay, fine. So now what happens when somebody arrives? Now here, there are a couple of ways to do this, but what I'm going to exploit here is the fact that if you remember our arrival process, one of its state variables was the number of arrivals, and that was a number that was increasing and never decreasing, right? So we can use that number, kind of peeking ahead a little bit, as the customer ID. So the first customer has an ID 1, second one 2, et cetera, et cetera. And we can get those numbers from the arrival process. But this component needs to know about. So what I'm going to do is I'm going to have an arrival event that that has an argument that's the ID of the customer who's just arrived. And whether they're increasing or not, as far as this component is concerned, it doesn't matter. As long as they're basically unique, that's the only thing I care. So what am I going to do? I'm going to add them to the queue. So instead of saying Q plus 1, now I'm adding it to this container, and now the size of the container is plus by 1. And as we'll see, then there are statistics objects that listen to containers and then do a time average of the size of them. So we'll see what that's about. All right. So now what else can kind of change as far as queue is concerned? Well, they can leave the queue and get service. And we've been calling that to the start service event. And you don't have to call it that, but that's a good name for it because that describes what happens. So we pop it off the queue and then just and that decreases the size of the queue by 1. That's like queue, when we were just counting, we decrease it by 1. We lose a server. And then, end service, again, the usual suspect. We get a server back, and then we have somebody who's actually completed service. And you could make a case for actually moving this state transition to start service, because in this model, once you start service, then you will actually finish service in this model. So you could make a case for moving it over here. So that 6 of one, half dozen of the other. The numbers will slightly change in a transient case, but if we run the system long enough, they'll pretty much be the same. And the difference between running it in transient versus a long time is something we'll cover later in the course. All right, so the final, so what we've done is we've taken care of all the state transitions for S, Q, and M. But what about R, the number of Renee? So none of the events so far have captured. When we start service, it's got to be on somebody who's kind of already there. So instead, we're going to have an event called renege, and I'm going to give it an argument, which is going to be the ID of the customer who's leaving the system. And the reason that's important is because different customers are going to have different times, and so somebody might come later who's more impatient, and so they may leave, and just so it'll be that one that leaves. So I want to know who it was, right? So now when the renege event occurs, I have one more renege, and then I'd better remove him from the queue. So what happens if I forget to remove him from the queue? Well, let's say he reneged, but then later they're actually going to start service, and then the model doesn't know that that's what we meant, and so that's just one of the reasons why. If you remember, like we kind of began the course doing all these things by hand, and then when we started implementing them on the computer, one of the first things I always talk about is run it in verbose mode, check your events, check your state changes, check all that. And all of that is facilitated by the verbose mode of the event list and by firing property changes or notifying state changes in Python, and then listening to them with this simple dumper thing, which, what that does is that eliminates the need for print statements. Say, well, how do I know if the state change is doing the right thing? Well, you put a print statement in, but then if I'm going to run it for 1 million time units, then I'm going to get 1 million print statements for each event. So I don't want that. So then I have to go in and edit the component, comment that out, And as I was haranguing last quarter, there's no such thing as a trivial edit. You have if your component is working right, then lock it up, shrink wrap it, don't touch it. And commenting out a print statement is touching it, so no touching. Okay, so all right, so let's. So now let's look at scheduling on this. So the scheduling is fairly straightforward. Okay, we've done this a lot of times. If there's an available server, we're going to start service, and then the kind of the high priority just for. I'm going to be at least at first a bit I'll be lenient about that, because that's, as I said, if you use continuous distributions, that's not an issue. Okay, so and then this condition here would be Q is not empty. That says empty for those until I did well on penmanship, but I don't think they even teach that anymore. And anybody have cursive when you were in elementary school? No, they still teach it. Anyway. So you see, I didn't do well at it. All right, okay. So what I've done, we picked off the easy ones here, but the model as it sits, even and now remember, we still need a directed path from a run, at least one run event to all events. Otherwise, they're not going to happen. In this case, assuming we have an arrival process like thing that's going to trigger this arrival event, that's the path from there. But as it sits now, this renege event is just kind of sitting out there waiting. So how can we deal with that? There are a number of different ways, but the most compelling that I found is that when we show up, it's like that's when our timer starts. So you can think of it, or just to, you can think of it like when, let's see, I don't know if you like classic movies, but have you ever seen the A Touch of Evil, the Orson Welles? If you like classic movies, anyway, just the opening scene of that, you see a guy get a bomb, turn a little timer thing and stick it in the trunk of somebody's car, and then you watch them get in the car, or watch another couple get in the car, they're driving along, and you see this. Anyway, so it's like when you show up, they hand you a bomb, and when you get to the server, they'll disarm the bomb. But if you don't get to the server, the bomb blows up. All right, so what is the bomb? The bomb is the renege event. And when does the renege event happen? Well, you remember we had this P sub R for renege. So that's our impatient time. This is how long I'm willing to wait. And if this renege event happens, then I'm going to leave. Now, this scheduling edge has an issue. Okay, so now what's wrong with the scheduling edge as it sits? It needs to pass an argument. Now, what argument is it? Well, if an arrival of an ID of I shows up, then when they renege, who's going to renege? That same I guy. So we need to pass this I here. Yes. No, it doesn't need to pass anything to start. That's the high priority. Yeah, sorry. Yeah. Sorry, well. Yeah, and that's it. There are some circumstances where we have to worry about that, so that's why I'm kind of introducing them for this particular model. It only comes up if you do something foolish, like you start using discrete distributions for your times and your service times, in which case you might get some time ties. But okay, so now here's the problem with the event graph as it sits now. Whoops, is that now how is this going to behave? Well, what's going to happen is some customers are going to go into start service right away and then get sort of taken off. For others, the renege, they may be in the queue for a while and the renege event will actually happen. But as it sits right now, both of those events are scheduled for that particular customer. And really, we only want one of them. Now, so you say, okay, how do we have only one of two events? Well, we had the if test, but we can't really do that because when a customer shows up, do we know whether they're going to get service yet before renege or renege before service? We don't know. I mean, that's the problem. The problem is that if we could somehow calculate that, then we could figure out which one would happen, but we can't do that because, you know, when you show up, there are a bunch of people ahead of me. How much time is that going to be? Well, it depends on the number of servers. It depends on their service time. It depends on so many things, but there's no formula for that in general. So now what's the deal? What did I say before? I said that, well, we got this time bomb, but the server has the key that will disarm it. So now what does that entail? That entails canceling the renege event. And so the start service event is going to cancel the renege event. But the problem, okay, and the problem is this, is that the renege event has an argument though, and canceling edges sort of have the same rule as scheduling edges. So if I cancel an event, start service says to cancel an event, but then renege says, hey, which one? Renege needs to know what the value of I is in order to remove it. And now start service actually knows what that is. I called it I, but I mean, so it knows I because it popped it off. So the guy that it popped off is going to be the one that gets canceled. So I'm going to cancel that one is going to be removed from the queue. And I have to say remove because it isn't necessarily the top one. Okay, and that's the model. Okay, so now we have a little issue though with the arrivals. So the arrival event by itself, and now it's keeping track of the number of arrivals, so it has our IDs in it, but it's not passing those IDs because it only has an arrival event with nothing in it. And so what we really want conceptually is something like this. So here are arrivals happening, and then basically taking this count, passing it to the arrival event. So now we have an event which matches this in terms of both name and arguments. And now we could write it like this, but the virtue of laziness says that since we already have an arrival event, we can subclass our arrival process and then simply override the arrival event and then schedule. Now in Java, we can do this. In Python, we have to do something. We have to give it a different name. Why? Because Python doesn't allow this. Why it doesn't is beyond me, but that's just... Okay, so now, all right, so I didn't show it here, but then the listener diagram is if we had one of these guys and then our server, and now he would just simply listen to it. So, and that's how it would. So every time this arrival event would happen, it would have as its argument the ID of the guy, that is the number of the customer, and then that would get passed to this arrival, and then things would kind of go on from there. Now, and the only problem now with this model, and we're going to fix it in the next couple classes, is there are other measures that I can't get from this model that I can't even get from Little's formula, as it turns out. So Little's formula even has its limits. What if I wanted to know, for those customers who got service, how long did they spend in the queue? And for those customers who reneged, how long did they spend in the queue? Those are measures that I would be interested in. I can't get that from this model. Now, what I can try to do is I can say, well, last time we kind of had this sim time that we used, and I could add that into that. So I could have like the arrival could have two, or like I would just need the one, but then I would need an additional container to have those times in it if I wanted to do that. And in order to kind of figure all that out, I would need to just kind of do a bunch of, it would be a little problematic here to figure out which was the time that this guy came in on, because those times are going to be double values. And then what's good about this is that the way that canceling edges work, it's going to, if I pass an argument, it's going to cancel the event that was scheduled with that value. But if I start saying I want to cancel an event with an exact double value, then that can be a little dicey, right? Because if it's off in the last bit, then it doesn't match. So now there's a way around that, and we will do that starting tomorrow. We'll see a way to get around that. Okay, so we've done that. Any questions about? Okay. Next model. So this is a simple machine repair model. So the scene is that we have a bunch of machines, and machines fail, right? I mean, there's no machine that doesn't fail. They haven't built a perpetual motion one yet. And in practice, not only do machines fail, but machines fail at the worst possible time. But and for this particular one, a lot depends on the facility. So if we're looking at our facility, these are each machine. These are not automatic type things. These are something. Oh, I don't know, like a drill press or a lathe or something where somebody's got to be actually watching the thing. And then furthermore, the machine operator is also their repair person. So if the machine fails, then the repair person's got to figure out what's wrong and fix it. That's the idea. This is the simplest possible model, though, of what's called a finite calling population. You've heard me use that word before. So let's see how that is different. So let's look at the parameters we have so far. So we have the number of machines, so I'll call that M. And when I say machines fail, well, okay, what do they fail? We're going to assume that there just be process, that the times to failure are basically in clock times. So and then it's going to take a certain amount of time to repair a machine, right? So, and then what about our state? Well, there's only one state I can think of, and that is the number of failed machines. Or I can think of the number of working machines that would be. And I'll, oops. I think I originally did it for a number of working machines, which is, so the number of failed machines is not going to be initially M. I'm going to assume they're all working at the start. Okay, yeah, so I'll have to fix that. It should be initially 0. All right, so as I said, this is the simplest model of this, and as you see, we're going to be expanding it as or maybe you'll be expanding. I think I'm asking you to expand it. So that's. I think that's the second problem that I asked you to do is like this, but with an extra twist. Okay, but again, we have one state variable, the number of failed machines, and what is the, in terms of our state. So we have, initially it's going to be 0, number of failed machines. And what causes it to change? Well, we're going to have one more failed machine when we have a failure event, and we're going to have one less failed machine when we finish repair. Now, one thing to note on this is that a lot of there are other ways of describing discrete event models like this. One other one is kind of more like a process flow type of thing, and just the orientation is a little bit different on those. So in those, time passes in the nodes. So like if I'm doing an activity of, say in this case, of repairing a machine, that would be a node in these other things. That, having said that, put that out of your mind, because in discrete events, all the time happens in between events. No time elapses during events. All of the state transitions are instantaneous. That's just something to think about. Okay, so here we have, like, if we have a failure, then we can schedule. It's going to take us I think I called it T sub R for repair, right? It'll take us that long to repair. And when we finish repair, it's going to fail again. So what is it that causes machines to fail? Repairing them. So if you don't want your machine to fail, never repair it, and it'll never fail again. I mean, just like computer, the IT people are always up in our grill about security, got to be secure. So there is one way that you can guarantee that your computer will never get hacked, and that is shut it off, lock it up in a safe, and never turn it on. And it can't be hacked. Okay? So if you don't want your machines to fail, don't fix them. But if you fix them, they're going to fail. That's just kind of what. Okay, so now, what's the dilemma here is that if we have M machines and they're all running at the beginning, then at some point they each need to have their own failure event. In other words, unlike the arrival process, which only has one arrival at a time, at the beginning we need to have M failure events happening, because like at the beginning of this, we're going to turn all the machines on and they're going to start failing. Which one is going to fail first? Whichever one has the smallest time to failure. Is that going to be the first one? No, it's going to be whichever one it is. We don't know which one that is. So how can we do that? So basically, what we need, and we've done this before, is we need our little friend, the init event, with our for loop, and that's going to look something like this. So in other words, here's what we've done already, but then to initialize this, we can do that again with our event graph for loop. I don't know why it does this, just a very sensitive thing. All right. Okay, so now our run event is going to schedule our first init passing at 0. And then, why? Because we're going to use the silly zero-based indexing thing. And and if you don't like that and you want to start from 1, then that would work too, except you would have to just sort of fix the ending condition here. Doesn't matter. The criterion is if you have one of these that produces exactly M of these, and for each init event, notice we're going to schedule a failure event with a time to failure on the scheduling edge. So at the beginning, as this is spinning, at the end of it, they're going to be, like, let's say we had 5 machines. At the end of this, there would be 5 failure events on the event list. And then whichever one happens to happen first, which could be any one of the 5, that one will go off. It'll schedule and repair. And then in the meantime, which is going to happen first, repairs or fail, just the event list is going to take care of it all. But now what's important to recognize here is that an arrival process is not going to work. So you might be tempted to have sort of to me, maybe I'll do it here. You might be tempted to do something like this. Right? So now, do you see what the problem is with this? I mean, among other things, the way it's written here, these failures kind of start coming. At some point, you could have more failed machines than you have machines. And that simply doesn't make sense. But more to the point, the other thing wrong with this is that the failures are kind of one at a time. In other words, one machine isn't going to fail until another one fails. And it's not even going to start failing until the other one fails. And that's not the way it works. The way it works is that they're all failing simultaneously. And it's whichever ones happen to, get there first are the ones that get it. Okay, so what's important about this is the finite calling population. And with the finite calling population, in almost all cases, we need to initialize it at the beginning with something like this, typically. Not a hard and fast rule, but what we can't use is an arrival process. That's the other thing. Like, look at the assumptions of an arrival process are that however many arrive to your system, the arrival rate is unchanged. But here, let's just sort of do some thought experiments on what this is going to look like. So let's say we had two machines. And so when they're the two machines are failing at a certain rate. And then now when one of them fails already, so now we have one machine failing, is it failing at the same rate as when two machines were failing? Okay, well, let's go all the way to an edge condition. Two machines failing simultaneously. What if they're both failed? What is the failure rate? What is the rate at which machines are failing when they're all failed? 0, right? Because if they're all failed, there's none of them are failing. So it's 0 versus, say, 5 machines failing. And that's going to happen at a certain rate. Or 2 to 1, for example, roughly speaking, the rate at which machines are failing when there is 1 versus 2 is half as much. The rate is about, again, you could quibble about the math. I mean, and you say, well, it depends on how long, but just in aggregate, when you have more machines failing, they're failing at a faster rate. And that's different than the infinite calling population, where no matter how many, if I had infinite number of machines, no matter how many fail, they're still going to fail at the same rate. Okay, infinity is just very weird, just so you know. Okay, so final model. And this is another very interesting one. Although what people find interesting, I've discovered for some reason, is a little different than things I find interesting. I'm not sure why that is, but as they say in the internet, your mileage may vary. Okay, so a tandem queue with blocking. So if you remember, we had a tandem queue model where we had sort of 2 servers. You left one server to go to the next. And there, we were assuming that both of those were multiple server queues. But if you remember, there was another tweak on our multiple server queue model that had finite capacity. And there we had balking, which is if a customer showed up and there was no room at the end, they left and we didn't see them again. So now we're going to look at another phenomenon called blocking. So what blocking is this, is that, okay, so we have our parts arriving to our system and they have to get processed first at one station and then at the other. But the first queue has infinite capacity, just a regular multiple server. We're going to assume that. But the second one has finite capacity. So now what does that mean though? I mean, now imagine manufacturing big things, I don't know, aircraft or something, so it's like, if you need, and I know they don't literally move, but I mean, it's still, conceptually there, you can have this kind of thing. In other words, if you, when you finish processing at the first station and the second queue is full, then you have to sit there. In other words, there's no room to move. There's no room to move off. So you sit there blocking that machine. So the machine now is finished processing. You're done with that, but you can't move off because there's no room to move forward. So that's that's fairly complicated. I mean, it's okay. So a part leaving the first station, you can only proceed to the second station if there's room in the second queue. And if the second queue is full, then the part remains on the first machine and it can't process another thing. So in other words, you're taking away that finite capacity in the second queue station is taking away from your ability to process parts. So now you have a server, a machine that is ready to process another part, but can't, so it's sitting there idle. So you're losing capacity, or, but not, I'm using the word a little bit differently. You're losing sort of processing power, or you're losing, it just sort of wastes stuff. And it's just like queues. The reason why a lot of this concern around queues is because queues are complete waste. Like when you're in a queue, why do you get a little antsy or upset when you're in the queue? Well, why are you in the queue? Because there's something that you want them to do, and not only are they not doing it, they don't even know you exist yet. So it's like, okay, I got to get this thing done, but it's like they're not seeing me. So your call is very important to us. Okay, so then, so we need, this is a, well, okay, so let's look at our parameters. We have our usual suspects, the number of machines in the first and second station, the service times of the first and second station, and now we have the second, the capacity of the second queue, and we're going to assume that's bigger than 0 because there's the extra little thing of, if there's no capacity whatsoever, then the model is a little bit different. Okay, so now state variables, we also have our usual suspects from before, which are the number in the queue at the first station, the number in queue at the second station, the number of available machines. I'm calling them machines because, but now, because of this extra phenomenon of being blocked, we're going to have an extra state variable, which is going to be how many blocked parts are there? I mean, in other words, how many machines are sitting idle and can't process even if there were available customers because a part is sitting on it. So that's an extra state variable that we need to keep track of. So now, with that in mind, we can kind of look at our events. Sorry, the heck? Every now and then it does this. It was doing fine, and then now it only shows up on here. So, all right. Now, we're going to assume an arrival process is going to be driving this. So we got a regular old arrival event here. Our run event is going to initialize all of our state variables as before. So we can start with that. Our arrival events, this by now, this is all the arrival and start service should be fairly familiar. But now here's the, well, let's look at the second station here. So here, this is even easier. This is the second station. When we arrive at the second station, who index is 1, we increment the queue. we decrement the queue and number of available servers, and then we increment those. So remember, once we're in service at the second one, we're doing okay. So we can, but what about our blocked variables? So here's the thing. When we finish service on the first station, we don't know whether we're going to be able to move off or not. And so in a way, by analogy to what we've been doing with queues, remember, a customer shows up to the queue, we increment the queue even if they're going to go into service right away, because we're just going to make that event very atomic. So when we finish service, we don't know if we're going to be able to move that part off yet or not. So instead of saying, okay, we're going to increment the number of available servers as we have previously, all we know when we finish service is that it's going to be blocked, and we may unblock it right away, but it's just going to be blocked. And we can only increment our available servers in the first one if we get unblocked. And when that happens, we get one less blocked machine and one more available server in our first station. Okay, so those are all the state transitions, and we can start filling in some of the, and again, we'll do the easy ones. And actually the easiest ones are down here, ironically enough. So, we've done all this. This is all, informs, now we're not, you want to be careful about not just sort of boilerplating things. We're doing this informed by what we have done before, but we're not just sort of blindly doing it. Okay, and then we can still schedule this, and this is going to take service time here. But the problem is now, when this event occurs and we have a blocked machine, can we always schedule this start service event? And the answer is no. Why? Yeah, exactly. We don't know if we can, or even just in the language of the model, because we don't have, we don't have an available server. So if S0 is still 0, and all we do is check the queue, then we could be going from 0 to -1. And that's now all of a sudden, what is -1 available servers? It means I owe you a server or something. That doesn't make any sense. Okay, so now, but now what can we do? What we might be able to do is we might be able to unblock. And how do we know whether we can unblock or not? If the second queue is less than capacity. So this is the second queue with index 1. If that's less than our capacity, then we can unblock. And now that we've unblocked, we have one additional server, and now we can schedule, maybe, if there's somebody in the queue, we can schedule one of those. But, and in addition, now that we've unblocked, that means that there's room in the next queue, and we can actually, at this point, unconditionally go here. The schedule, but we don't go anywhere. We can schedule the arrival, and we know we can execute it because we have checked to make sure that it's less than that. So I hope I got that right. Okay. Oops. So that's what the final thing looks like. So now, as you can see, in the bottom, in the lower, so for the second station, it looked very similar to what we've done before. But look at the first station. Now that we have this extra event in there, So it doesn't follow the same pattern. So the lesson is, you don't just sort of boilerplate anything that it's dictated by the state transitions and who gets to schedule what and what the conditions are. Okay. Questions? All perfectly clear. Okay, so what we've done is we've added some features to these. We have the use of containers. We had that canceling edge in the Reneged model. And then we had our finite calling population and introduced the idea of blocking. And then now tomorrow, we're going to take it up another notch. So we'll see that then.
I do have one, I guess, observation / question, Dr.
Yes.
So Reneged versus bulk. Reneged is like after a certain period of time, and bulk is just if the line is too long. Is that
Correct.
about right? Okay.
Yeah.
Just making sure I have that difference solidified. Thank you.
Yeah. In other words, Reneged happens after you join the line. Bulking happens before you join the line.
Cool. Thank you.
Okay. Any other questions? Okay. See you tomorrow.